Hey everyone, Chang here and welcome to my channel. Today the video is going to be somewhat more difficult, right? We're focusing on proof, but the most common proof that we actually see is what we call direct proof. You have whatever you're given and then what you want to prove. And usually they expect you to have sort of a straightforward step-by-step path from beginning to end, right? That's the most common one that we see in all the textbooks, in actually a lot of the exam questions, and just in general what they expect of you. Even though there's a bunch of different ways to prove, this is one that is most commonly used and most difficult to grasp. Now, the reason for that is because it paints this negative notion that you have to be able to see all the steps right away. And usually that's not the case. What we don't see in all of these really well written step-by-step proof is the scratch work behind it, right? What is the thinking process that they got from the beginning to the end? So hopefully with this video, I can actually shed some light on it. I'm not that great in proof in any way, but at least I have a general idea. So every time you experience a proof like this one right here, you should question yourself first and foremost, what are all the information they've given you, right? After that, remember every single definition, because most likely a lot of the proof that you're going to encounter is based on your thorough understanding of what those definitions are. And once you understand those definitions, it gives you a boundary of how to go about it. So let's look at this, for example. Let x be an element of the real number. So this right here, we already know is x could be any possible number. But if x is less than 0, so that's a key information, right? It's putting a condition there. If x is less than 0, then we want to prove that x squared plus 1 is going to be bigger than 0. In other words, if x is a negative number, then x squared plus 1 is a positive number. So how can we go about it? The only real information we are given is this. So this is most likely the key that we have to go about. Well, we know this. If x is less than 0, then we know that x, well, let's just make sure it looks somewhat like an x, is some negative number. Okay, that's all we really know. Well, if we're trying for the end result to be something like this, let's just look at what happens step by step and think about this. How can we relate x to x squared plus 1? Well, let's just see what happens with x squared. X squared is basically this number times itself. A negative number times the same negative number. Okay, now that's actually getting us somewhere, because guess what? Two negative numbers, if you multiply them together, negative times a negative is positive. So technically, this right here gives you the number squared, where this is positive. Okay, now we're getting somewhere. Well, what else? This is not what we want. We want to work with x squared plus 1. Well, we know that x squared is going to be a positive number no matter what. Now, if that's the case, x squared plus 1. This is positive. 1 we know is positive. So two positive number, unless you know we live in a clown world or something, right? Two positive number, when you add them together, the end result is still some positive number. Well, if it's some positive number, if this right here is some positive number, then yes, there it is. Your proof is done. Some positive number, by definition of the fact that it is positive, is definitely going to be greater than 0. So hopefully with this, even though it's fairly simple, start off with only what you're given, figure out what it's really saying, and then start playing around with things. Guess what? If we didn't jump to x squared right away and we jump to x squared plus 1, it could be a little confusing to try to justify it, right? But that's just all scratch work. So let's look at the next one and see if we can go about trying to prove it directly. All right, so here's our next problem. Now this one is a tad bit more challenging than the first one. The first one, you were only limited to one given information. This one requires you to know a little more information. If n, some random variable, right, is an odd integer, so we got to make sure we know what an odd integer is, then 3n plus 5 is even. So at least we know with this problem right here, if we want to prove this, we have to know specifically by mathematical definition what an odd integer is and what is even. Well, luckily for us, we have this common saying that if it's odd, well, it's not divisible by 2. Duh. But basically, we already have an intuitive sense, but there is a mathematical definition of odd integers. Now, there's 2, and you can use either or, whichever one you want that is easier to use. I always like the fact that basically for anything that's odd, right, the number can be written as basically 2k plus 1. So it's going to be 2 times some number plus 1. That's what an odd integer is, right? And let's just say k is an element of, we're talking about integers, so let's just say they're integers. Okay, so that's what odd integers are. Even, well, if you guys can sort of guess, anything that could be divisible by 2 or by mathematical definition can be written as 2 times some number, k, where k is an element of, let's just say, integers as well. Okay, cool. So that's what odd and even mean. So by understanding these two definitions that are being used to prove this statement, then we have something to work with. Well, if n is an odd integer, so if that's the case, we can say n equals 2k plus 1 based on the definition of odd right here, right? That's how we got this, okay? Well, if that's the case, we're working with 3n plus 5 and we want to prove that it is even. Well, for something to be even, that means it must be 2 times some number. If we can show that 3n plus 5 is always going to end up being 2 times some number, then we know that's even. So we have this one right here, and we want to work with this statement, 3n plus 5. Well, there's n. We think n is this somehow. Let's plug it in. Now we have 3 times 2k plus 1, where this originally was just your n, right, plus 5. Okay, and then we distribute, of course, this out, and then so we have 6k plus, what's that, 3 plus 5. Okay, well, definitely combine like terms. These guys right here, that's just 6k plus 8. Hopefully at this point you guys can sort of see it, right? All right, remember, I want to prove whatever this end up being is something 2 times some number. Well, we have a 6k and we have an 8. So if we have 6k and 8, then that means technically, if we want to show explicitly that it's even, we need 2 times some number. We can factor out a 2 from there. So that's technically just 2 times, because we took a 2 from here, that's 3k plus, took a 2 from here, 4. We know that this is still going to be some number. Now we have 2 times some number. So that means in the end result is 2 times some number, showing that 3n plus 5 is even if n is an odd integer. So remember, we started off with the assumption. They're saying that if n is an odd integer. If it's not, then of course this whole proof is utter nonsense, right? But we've shown using, basically assuming that n is an odd integer because the statement gives it to us, then we are finally able to prove that 3n plus 5 is an even. Alright, so let's look at this problem right here. Now this is structured in a way as one of those problems where the first time you look at it, you're like a deer in the headlight. What the heck is it asking? There's so many symbols. What's going on? The best thing to do when you approach this problem is, of course, read the entire problem. What the hell is it asking, right? And then afterwards, start trying to understand each and every one of these small little components. Well, first and foremost, let's just look at this. G equals this little curly bracket, 1, 2, 3. What this is actually saying is that there's this bag or this container named G, and inside this container or this bag, there's 3 numbers. 1, 2, and 3. That is it. Nothing special about that. And now we have n is an element of G. That means n is one of those three numbers. So even though this looks very complicated, what it's saying is that you have this container with these three numbers, 1, 2, and 3, and n just represents that it could potentially be 1, it could potentially be 2, it could potentially be 3. That is it. Now let's look at the next part. If n times n plus 3 divided by 2 is even, then n plus 1 times n minus 5 over 2 is even. That's what we want to prove. Okay, well, the n is just basically the n as an element of G. So basically n is 1, 2, and 3. We're saying that if this right here, this entirety is even, then this is even. That's what we want to show. Okay, well, if we don't know what else to do and we know that n is going to be one of those three numbers, why not just test them all? Let's just do the first one. N equals 1. So if I were to plug this in here, technically what I have is just 1 times 1 plus 3 over 2. That's 4 over 2. That's 2. Okay, so this one is telling me at least this section, right? This section right here is even if I use n is 1. Well, what happens if I use n is 2? Because n could be possibly 2 or 3. Well, if that's the case, what do I have? I have 2 times 2 plus 3 over 2. That's just 2 times 5 over 2, which the 2 cancels out. So the end result is still 5. That's odd. Okay. Well, let's look at the third one. Third possibility, n equals 3. So basically I have 3 times 3 plus 3 over 2, which is just what? 3 times, that's 6 over 2. That's 18 divided by 2. That's 9. This is also odd. Okay. Well, guess what? I don't care about this. I don't care about this either. Why? Because the only thing I'm paying attention to is if this statement right here is even, then I want to prove that this right here is even as well. Well, for n equals 2 and n equals 3, they're odd. The statement's odd itself, so it doesn't matter to me. I only care if it's even. And the only one that makes it even is this one right here, where n equals 1. All right, well, if that's the case, and since n can only be these guys, let's just plug in 1 and see what happens. Well, if we're looking at this, it's just going to be 1 plus 1 times 1 minus 5 over 2. That's 2 times negative 4 over 2, or the end result, if the 2 just cancels out, right, we have negative 4. Well, negative 4 we know is even because the definition of even number, once again, is any number that can be divided by 2 or written as 2 times some number. This number, negative 4, is clearly a number that could be divided by 2 or can be written as 2 times, well, guess what, negative 2. So, even though this is kind of odd, right, it proves it shows no real purpose other than just teaching you proof, right? But it works because we looked at only the scenario that it could potentially be even, and that's only one of them is when n is the number 1, right? Everything else is still odd, but it does show that if this statement is even, the end result, this statement right here, is also even, and just like that, this is proven as well. All right, so we reached the end of this video, and hopefully with this, even though, yes, I've shown you guys proof problems that are sort of not all that useful, probably not ones that you guys would normally see on a regular basis, but I'm hoping that to highlight some of the key concepts or approaches to direct proof. Once again, every time you see a proof and you're required to prove it directly, right, look at what they give you. Is there definitions that you can recall? Odd, even, I don't know, whole numbers, integers, so on and so forth. Just see what they give you. Then after that, based on the definition, and my recommendation is just write it all out. So this is almost like a piece of a puzzle that you can sort of just play around with, right? The other thing that we have to do is make sure we look at what the condition is, because normally proof is not a blanket overall statement that applies to every possible scenario. There's always a certain requirement for some end result to occur. So for example, in this one right here, this final statement where this is even that you want to prove only occurs when this original statement right here, this requirement, is even, right? Each and every one of those proofs are like that. There's always a given assumption. So if you know what the given assumption is, and you look at it, and it built on that, built on the definitions that you know, then most likely you'll find some sort of path, some sort of a way to prove the statement is true. Unless, they say prove it's false, then that's another story, right? To show something is false is actually a lot easier than proving a statement. So we'll go into that in another video. Thank you for watching this video. Please like, comment, and subscribe. I will see you in the next video.